Hello everyone, welcome back to 3 Deviations. So we spent a lot of time talking about optimization. Over the past, I think, 6 videos we talked about optimization. That was the capstone of Unit 3 really, to talk about applications of differentiation. But we've got another one that's pretty important called Newton's method. And this is actually a really cool method that allows us to find zeros of polynomials, or at least approximate zeros of polynomials. And I think it's a really cool application that we have of differentiation that's actually pretty helpful to some more lower level math that we see maybe in a pre-calculus class. Of course, a prerequisite for this is some basic differentiation knowledge, otherwise we should be good. So let's get started. So basically Newton's method thinks about finding zeros with derivatives. So if I have a function, a polynomial function, with an order higher than, with a leading term, with a degree higher than really 2, there's no real easy way to solve for the zeros. Now, of course, there is a way. There's the cubic formula, which is ridiculously long. Then there's the rational roots theorem, synthetic division, and Descartes' law of signs, which is also really long and tedious. And it gets even worse as you go to higher and higher order polynomials. And then you need to add in the fact that you can't solve a polynomial with a degree above 4. There's no formula to find all the zeros, and then the rational roots theorem only solves for rational roots. It doesn't tackle irrational stuff. So we have this thing called Newton's method in calculus that allows us to approximate not only the rational zeros but also the irrational zeros of a function. Now I say approximate because this isn't perfect. Or well, maybe in the limiting case it is, but we don't want to be that tedious here. So I'm going to illustrate what Newton's method looks like. So it's going to look like we've got x squared up here. Let me draw in a couple tangent lines. Now, what's really going on here? Well, so basically, I am picking some points, right? So I'm picking some test points. The first test point I've chosen was 2. So I chose 2. And then basically what I'm supposed to do is I draw a tangent line. That's this green thing here. And this tangent line here is going to give me my first approximation for a 0. So the real 0 of x squared is just actually 0. It's the origin. So we've gotten closer. So this is x naught, our approximation here, x naught. Then this is going to be our approximation x1 or x2, and then this is x1. I'm going to call that x naught. And then if I want to make another approximation, I go up here at 1, and then I draw another tangent line, which we see in yellow, and that gives me another approximation. That'd be x2. And you can see this gets closer and closer to 0, but if I draw enough tangent lines, it's basically going to get there. So that's how Newton's method works. It takes in tangent lines, and the nice thing about this is basically you find the derivative, you decide the function, you plug it into this formula, and then you are all set. You just got to plug some numbers into your calculator and plug and chug, and then you will be left with however many approximations you want. So let's actually talk about the math behind this. So Newton's method basically says that if I have my first approximation, let's call that x of n. Let's say that's an approximation I've made. And then if I subtract the value of that function at x of n over the derivative of that function at x of n, I'm going to be given my next approximation, right? So then I'm given my next approximation there. And then you can see this goes on, and I can keep plugging into this formula here, and it will keep getting better and better. And again, in the limiting case, it's going to approach our root as we take more approximations. All right, now as good as Newton's method may seem, there are actually a few caveats. So one of the main ones is, if I have a function here, I want to find the zero. Well, I shouldn't pick these 2 points because those are going to be awful approximations because they're never going to hit the x-axis. Even if I pick one with really shallow slope, that's not going to hit the x-axis. We want to pick points that we think are probably going to give us steeper slopes, because the steeper the slope is, the closer we get to that zero. So we want to take approximations that are going to make sense. Like, we don't want to take it where our derivative is going to be equal to 0. We don't want to take it where our derivative is going to be really, 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 really small. We want to take it where our derivative is fairly large in the positive or negative magnitude, and that will give us a good approximation. And then we can do further order approximations, and that will make it better. All right, so why don't we do an example? So we're actually going to see how this works. So we're going to take the third approximation of x cubed minus 2x minus 5 equals 0. And we are going to set up our x of 1 is 2. So we already have our x of 1. So we can use that formula. But first, why don't we find the derivative? So we know f of x is equal to x cubed minus 2x minus 5. Taking the derivative of this is really easy. We just reduce it. So we get f prime of x is going to be equal to 3x squared minus 2. Okay, so now what we are going to do is we're going to plug it into the formula, and we're going to find x of 2. So x of 2 is going to be equal to x of 1 minus x of 1 cubed minus 2x of 1 minus 5 over 3x of 1 squared minus 2. All right, and we already know x of 1, that's 2, so we're just going to do 2 minus 2 to the third minus 2 times 2 minus 5 over 3 times 2 squared minus 2, and that's going to be 2.1. So there is our x of 2. Now we need to find our x of 3. To do this, we just do it again. So now we're given x of 3 is equal to x of 2 minus x of 2 cubed minus 2x of 2 minus 5 over 3x of 2 squared minus 2. And that's going to be 2.1 minus 2.1 cubed minus 2 times 2.1 minus 5 over 3 times 2.1 squared minus 2. And that's going to give us 2.0946. And usually in these examples, they'll probably give you some sort of decimal approximation, however many decimal points they want you to go to. I don't think sig figs are very important. This isn't a chem class or anything. And of course, we should probably be writing that this is an approximation for that, because we are kind of still going off our calculator, doesn't actually stop there. So that is how Newton's method works. It's a pretty nifty trick, I would say. Maybe we'll do another few examples in the next video, and then we will be off to talk about a new type of calculus. So thank you for watching, and we will see you guys in the